Howdy. We're going to do another lesson on limits. This one is going to be about limits involving infinity. That means that we might be plugging in infinity. We might be getting infinities for answers, stuff like that. So let's get to it. Got to flip my computer here. So one thing that can happen that hasn't happened a lot yet is you can have limits that just don't exist. And so one of the things that causes a limit to exist is one of three things. F of x approaches a different number from the left and the right. F of x increases or decreases without bound in the neighborhood of C, or F of x oscillates between two fixed values as x approaches C. And you're going to see that happen a little bit today. So we are going to have some limits that don't exist, and that's okay. Mathematicians don't like it when things don't work out, so we try to describe it as much as possible, and that's what we're going to do. So right here, I have the limit as x approaches 3 of x minus 3 over the absolute value of x minus 3. So with this, honestly, I just want to show you graphically what something like this looks like. If I were to graph this, when x is greater than 3, both of these are already positive, and they're going to be at the same number, so I'm really just going to be at 1. Okay, I meant to make that a whole, but it didn't work. When x equals 3, this is 0 over 0, which means 3 is not part of the domain. So I have this. And when x is less than 3, like 2, I would have negative 1 over 1, which is negative 1. That absolute value function is a step function. And if I find the limit as x approaches 3, if I follow my fingers along there, my fingers are not going to touch near 3. So this limit does not exist. Okay. Over here, I have the limit as x approaches 2, and if I were to plug in 2, I'd get 8/4 minus 2 over 4 minus 8 plus 4. I get 0 over 0, so maybe I can cancel things. All right, let's see. I'm going to multiply the top and the bottom by x squared, because I don't like that complex fraction. And then I'm going to create, let's see, this would be 8 minus 2x squared over x squared. And this, if I wanted to factor, would be x minus 2 squared, which up here I can factor out a 2, which factors even more. 2 times 2 minus x, 2 plus x. And this guy could leave a negative 1 behind. Okay, so now if I simplify this, I have the limit as x approaches 2 of negative 2 times 2 plus x over x squared times x minus 2. I still have an x minus 2 on the bottom. So when I go to try to evaluate this, it's still undefined. And since it's still undefined, that means this approaches some kind of infinity. Maybe a positive infinity from one side, maybe a negative infinity from the other. Let's find out. So if I come from the right of 2, up here I'm going to have basically negative 2 times 4. That'll be negative. And down here, slightly to the right of 2 would make this close to 0 but positive. So a positive close to 0 times 4. So what I really am going to have is I'm going to have a negative on top and then a positive itty bitty number on the bottom. So a negative big-ish number divided by a teeny tiny positive number is going to be a really big negative. The limit as x approaches 2 from the right is going to be negative infinity. If I approach 2 from the left, I'm going to still have a negative on top, but I'm also going to have a negative on the bottom, which means I'm going to approach positive infinity. I'm sorry how messy this is. I'll try to be better. Those don't match. So this limit as a whole does not exist. And it's because it goes to both a positive and a negative infinity. Okay? So what do I do if instead of the limit approaching infinity, I want x to approach infinity? Now, this is one of those times where there's rules, and I want you to know the rules, but I want you to know why they work. So we are going to talk about my favorite rule, which is the spit in the ocean rule. Didn't think I was going to say that. When x increases or decreases without bound, in other words, x approaches positive or negative infinity, evaluating a limit results in the end behavior of a function. That means, does it approach a horizontal asymptote? Does it just shoot off into the space? Does it wiggle? I don't know. When the limit results in a numerical value like 4 or 2 or 0, it can be said that the function has one or possibly two horizontal asymptotes. The line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit for x approaches infinity goes to b or the limit as x approaches negative infinity goes to b. You gotta check both. Okay, so horizontal asymptotes, you check for those by letting x go to infinity. Also, you have to look at both of these limits, x approaches infinity and x approaches negative infinity, to test both sides, because there are plenty of things that have two horizontal asymptotes. So when you are trying to evaluate the end behavior of a rational function, and a rational function is a polynomial over another polynomial, we can make some generalizations. If the degree of the numerator and the denominator are equal, then the horizontal asymptote is going to be y equals the ratio of the lead coefficients, or y equals a over b if you want to give yourself something quick to look at. So if the numerator and the denominator are the same degree, you take the ratio of the lead coefficients. Those are the coefficients in front of the highest powered term. If the degree in the denominator is greater than the degree in the numerator, then the horizontal asymptote is y equals 0. And if the degree in the numerator is greater than the degree in the denominator, then there is no horizontal asymptote. Okay, I said a phrase and I haven't talked about it. Spit in the ocean rule. What are you talking about, Mrs. Vibber? Well, this is what I'm talking about. Why do those rules work? I know you looked at them last year, at least I think you did. Why do they work? How come you can just compare the degrees and forget everything else? Because of the spit in the ocean rule. If you're on a boat or on the beach and you spit in the ocean, does the level of the ocean rise? I mean, technically, yeah, but nobody cares. Because for all intents and purposes, there are an infinite number of atoms in the ocean. Yes, I know it's not infinite, but it's a gigantic number. You spitting in that ocean does not really affect that gigantic number at all. So as x approaches infinity, what we really do is we look at this and say, you know what? As x approaches infinity, these things don't even matter. Nothing matters but the highest powered term, or but the highest influential piece of the numerator and the denominator. So you can ignore the rest because it's like spitting in the ocean. And literally, the limit of this rational function is equal to the limit of 5x cubed over negative 4x cubed. I'm not simplifying that expression. I'm just saying ignore the stuff that doesn't matter, because as x goes to infinity, those limits are equal. And if they are, now I can simplify in here and say, you know what? That's the same as the limit as x approaches infinity of 5 over negative 4. And since there's no x left, I now have my answer. It's negative 5/4. So this gets at that rule that if you take the limit as x approaches infinity, you just look at the highest powered terms, and then you compare the ratio of their coefficients. That's it. If I come over here, x is approaching negative infinity, so I'm going to be a little bit careful here, and I'm going to just look at the highest powered terms again. This doesn't matter, that doesn't matter. So this limit is the same as the limit as x approaches negative infinity of 5x to the 4th over negative 4x cubed. And that would be the same as the limit as x approaches negative infinity of 5x over negative 4. The top is bigger than the bottom, so when I plug negative infinity in for x, my numerator is going to be negative infinity divided by negative 4, which is positive infinity. Okay, rewind, do it the quick way. As x approaches an infinity, you want to compare the highest powered terms. If the top has a bigger power than the bottom, then it's going to go toward infinity. And you know what? I should probably come back here and say if the top is, if the degree in the numerator is greater than the degree in the denominator, then there's no horizontal asymptote, and the limit equals positive or negative infinity. Just depends on what's going on. I hit the wrong button. Oh no. There we go. Okay, let's take the shortcut this time. X is going towards positive infinity. I'm going to compare the degrees. The bottom degree is bigger than the top. That means the bottom infinity is way bigger than the top infinity. So I have a large number on top, but a gigantic number on the bottom. I've got like infinity divided by infinity. So I have a fraction that's really small, and really small fractions are effectively zero. So this answer is 0 because the degree on the bottom is bigger than the degree on the top. Over here, I can still compare degrees, even though this isn't technically a rational function. I can still compare the degrees. So this is the same as the limit as x approaches infinity of 3x over root 2x. Because the square root of 2x squared is like the square root of 2 times the square root of x squared. Mrs. Bibber, you forgot something. Yes, I did. When you square root an even, you got to give that thing absolute value. Okay, now x is going toward positive infinity, so that absolute value isn't really necessary, but it's there. And I have x and x, so my degrees match. And this limit goes to 3 over the square root of 2. And guess what, kids? You're in calculus now. You don't need to rationalize the denominator. Yay! You're welcome. All right, last thing. Now let's look for horizontal asymptotes. So if I want to find horizontal asymptotes of funky things that are not rational functions, I just have to look at the limit as x approaches infinity and negative infinity and just kind of use my noodle a little bit. So I'm going to take the limit as x approaches infinity of this thing, 2 over 1 plus e to the x minus 1. And now I'm going to use my noggin. If I were to plug infinity in for x, that's going to be 2 divided by 1 plus e to the infinity. Okay? 2 over 1 plus e to the infinity minus 1. That's going to be like 2 over infinity minus 1. And 2 over infinity is effectively 0 because it's a really, really, really small fraction. So that's 0 minus 1, which is negative 1. Since the limit as x approaches infinity equals negative 1, therefore, y equals negative 1 is an asymptote. Now let's try negative infinity. The limit as x approaches negative infinity of 2 over 1 plus e to the x minus 1. Let's see. Well, that's going to be 2 over 1 plus e to the negative infinity. Okay. E to the negative infinity is 1 plus 1 over e to the infinity. So that's going to be like 0. 1 over e to the infinity is like 0. 1 plus 0 is 1. 2 divided by 1 is 2. Minus 1 is 1. Whoa, that's crazy. That means y equals 1 is another horizontal asymptote. Crazy. All right, let's come over here. For some reason, this didn't print, but I'm pretty sure it's supposed to say sine x. I want to find some horizontal asymptotes here, so I'm going to take the limit as x approaches infinity of 3x plus sine x over 2x minus cosine x. What? As x approaches infinity, sine does this. It oscillates, right? But here's the thing. Sine oscillates between 1 and negative 1. So up here, when I plug infinity in for x, I have 3 times infinity. And then I'm like adding 1, subtracting 1, adding a half, or subtracting a half. Nobody cares. This is like spit in the ocean. Same with the cosine on the bottom. So this is the same as the limit as x approaches infinity of 3x over 2x, which is 3 halves. So y equals 3 halves is one of our asymptotes. Now I'm going to do it again toward negative infinity. 3x plus sine x, 3x minus cosine x. And guess what? The same thing happens. If I look at the other side of sine and cosine, it goes to-do, 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 and it oscillates between 1 and negative 1. So nobody cares because I'm plugging in an infinity for x. So I have the wrong number in here. That should say 2x. Pardon me. So I have the limit as x approaches negative infinity of 3x over 2x. And really, those x's don't even need to be there. I still get 3 halves. So this has one asymptote at y equals 3 halves, and the graph approaches it on the right and on the left. Okie dokie. Down here. Whew. How long is this video right now? I don't even know. Trying to finish it quickly. I should do a different color. Purple. Limit x approaches infinity. 2x cubed minus 9 over x cubed minus 5x plus 1. The absolute value I can ignore because as x approaches infinity, that's going to be positive anyway. So really, I'm just comparing these two things. They have the same degree on the top and on the bottom. So that equals 2. As x approaches negative infinity, that numerator is going to be negative. So it's going to need to get negated. So really, piecewise, this becomes negative 2x cubed plus 9 over x cubed minus 5x plus 1. Now, when I compare these, I get negative 2. So we have asymptotes at y equals plus or minus. Oh, come on, OneNote. It's doing that thing again. Things disappear. That should say plus or minus 2. Write it down. All right. And then last but not least on this one, I'm going to take the limit as x approaches infinity of sine x over x. Think about the spit in the ocean rule. Sine is just bouncing between positive 1 and negative 1, but then I'm dividing it by infinity. And you're thinking, wait, but that'd be positive 1 over infinity, negative 1 over infinity. Those are both small fractions. And all small fractions are tending towards 0, and 0 is a non-signed number. So this goes to 0. And if I take the limit as x approaches negative infinity of sine x over x, I get the same thing. Positive 1, negative 1, kind of bouncing in between, but I'm dividing by negative infinity. Tiniest number divided by a gigantic number, going to head towards 0 again. So y equals 0 is our last asymptote. All right, dumb joke time. Again, I got really bad ones today. What did the janitor say when he jumped out of the closet? Supplies! That's it. That's all I got today. So I hope you learned something about limits and ask me questions if you have them.